This video looks at covariant differentiation, in particular finding the derivative of a vector in a curved space. Let's say we're given some vector field over some part of a manifold. We can find its derivative with respect to the points in the manifold if we first perhaps begin by writing it out in its component form, its contravariant components, and its covariant basis. And so the derivative then, just using the product rule, standard product rule that we all know and familiar with, gives us the derivative of the vector components times the basis plus the components times the derivative of the basis. Now the last term normally doesn't appear when we're talking about flat space, the usual partial derivatives of things. When we're working in flat space, basis vectors are all constant, just like in the image here. The basis vectors don't vary from point to point, they're the same, they're constant everywhere throughout the manifold, or at least in some region of the manifold, and so the derivative of the basis vectors is 0. Very simple. And so that just gives us the familiar result for the outcome of derivative of a vector, or partial derivative of a vector. It's just the partial derivative of the components of the vector. Very straightforward, and what we're used to. In curved spaces though, the story is very different. As the coordinate axes show, the basis vectors change throughout the entire region. They're not constant anywhere, they vary from point to point. And so there's a rule for this, and it turns out the partial derivative of the basis vectors, in general form, gives us this gamma term over here times the basis vector. And this is called the affine connection, or the connection coefficient, or Christoffel symbol of the second kind. And notice the Einstein summation conventions in operation here. We have an upper index and a lower index over which we must sum. So this produces a set. For any given basis vector, its derivative will produce a set of other basis vectors times this constant out front. Alright, so for a covariant basis vectors, this is the result here. Important result to remember for contravariant basis vectors is this result over here, the negative here. And again, we're summing over mu. Alright. And that's the difference between flat space and curved space. The basis vectors change everywhere in a curved space. They are constant everywhere in a flat space. Alright, so using these symbols, so let's go and find the derivative of a vector. Here we are, we've got our vector and we take the partial derivative of it. And in general, this expression plus this. And what we can do now is we can factor out the basis vectors by relabeling them. These are dummy indices. They don't have to be labelled mu, they can be labelled anything else. We can swap them with the alpha. So mu and alpha can be interchanged as dummy indices, and that then gives us E alpha here, E alpha over here, factorise it out, and what we're left with is the covariant derivative of the components of the vector. And this bit in the brackets here, the covariant derivative of the components of the vector, is generally expressed in this form down here. Okay, where again this notation here is just a shorter version of saying the partial derivative of V alpha with respect to x beta. For the case of the covariant components, these were the contravariant components. Let's have a look at the covariant components. Again, this rule applies here, and it comes from the previous page there, where these basis vectors produced a negative affine connection, or the derivative of the basis vectors produced a negative affine connection. There's one exception here. If we've got some scalar function, call it psi, the covariant derivative of that is the same as the partial derivative, because a scalar has no basis vectors. It doesn't depend on location. And so the covariant derivative is equal to the partial derivative for this particular case, for any sort of scalar quantity. Alright, now the quantity del, or nabla beta V alpha, is a tensor of rank 2. That's the two indices here would suggest the alpha and the beta would suggest it's a rank 2 tensor. But this can be written in general as del V, or nabla V, where the nabla is e to the alpha d alpha, so that del V, or nabla V, is this expression here. So here's the basis vector, here's the derivative, so that's the operator del. This is the tensor product, outer product, if you like, the tensor product, and it's a product of the basis vectors and some components. This can be rearranged, and we can keep alpha over to the left, and over here we want the partial derivative or covariant derivative of this whole business here. That's the components and the basis vectors. And that will give us the covariant derivative of the contravariant components, then expanded in the basis here. Alright, so if we differentiate this second rank tensor V, second rank, we can see the two components here, so rank 2. Let's write it out in this basis form. So del V is e to the delta, so there's our operator, del or nabla. Outer product with this business here, and this is the bit we're going to be interested in here. Move the partial derivative over. We want the partial derivative of all of this. Find how this changes. Okay, so let's have a look at the next line down. Here's the partial derivative of this object here. Alright, first bit, partial derivative is straightforward. Alright, we're used to that. Then, by the product rule, we want the partial derivative of the first basis vector, E alpha. And then we want the partial derivative in this last section of the last basis vector. Now, using the affine connection, we can write this out, no change to the first term here, but over the second term, this d delta E alpha becomes this gamma mu alpha delta, expanded in the E mu basis, outer product with E beta, and this gives, and over here, same thing here, d delta E beta, it gives us this gamma beta delta, and then expanded in the mu basis. Now, one important thing is we're going to go now from this third line to the fourth line here, we're going to swap dummy indices. Again, there's two alphas, two mu's. We'd like to expand it in the E alpha, E beta. So I'd like to get rid of the E mu here, and really, an alpha up, alpha down, mu up, mu down, they can simply be swapped. And what we end up with is V mu gamma alpha. And this changes to an E alpha. Same thing over here, we can change this, there's the mu up, the mu down, the beta up, beta down, swap those two because we want to produce E alpha and E beta, and they factor out. This bit in here is the covariant derivative of the second rank, of the components of the second rank tensor from up here. Here it is. So the covariant derivative of the contravariant components of the second rank tensor here. Alright, this can be written as delta V alpha beta expanded in the basis E alpha E beta. Very important, notice the index there. Alright, so finally this is now a third rank tensor. You can see 1, 2, 3 basis vector. These three basis vectors, the outer product of them forms its own basis, a third rank tensor, expanded in the basis. Alright, next thing, by expanding out a tensor product in terms of its outer product, its basis vectors, it becomes relatively straightforward to find its covariant derivative. So those little basis vectors are going to be really handy in helping us find things. They make our life a whole lot easier. If you can expand an object in terms of its basis vector, the outer product of its basis vector, you can go through them with the product rule, the Leibniz rule, whatever you want to call it, run through that and find the derivative of each of them and express it as an affine connection. Alright, so let's have a look here at a two-dimensional example here. In polar coordinates, some vector expressed contravariant components, VR, V theta. Alright, now the ER basis is cos theta EX plus sin theta EY, probably familiar to many people. E theta is minus R sin theta EX plus R cos theta EY. Right. The derivative of the basis vectors, dE, R, dR is 0. The derivative of this object with respect to R, no R's in here, so that's 0. That implies the connection coefficients or affine connections are all 0. This basis, the derivative with respect to theta, well, that's going to be something, isn't it? So we end up with an affine connection of 1 on R by E theta. That implies that gamma theta R theta is 1 on R and gamma R R theta is 0. Carrying on the same way would be familiar if you find the derivative of E theta with respect to R, this one here, we'll get 0. The derivative of E theta with respect to theta, again, you'll get 1 on R. this one minus r, this one 0. And when you do that, work out the covariant derivative or the components of this vector with respect to r. We expand this out, we end up with this object here, expanding that out, and one of these, this one here, as we saw earlier, just drops out altogether. It drops out because of this rule here. That coefficient is 0. We're left with just this one, which is, if you match it up the top there, it's this one here. And so the covariant derivative of this vector in polar coordinates with respect to r is this object here. And that's how covariant differentiation works. It happens because the basis vectors vary from point to point, and so the derivative must take that into account. And that is the idea of covariant differentiation. In flat Euclidean space, all these affine connections or connection coefficients are all 0. They disappear. You don't have to worry about them. The text of all this presentation, I'll attach as a PDF to this video. Okay, well that's it then. Done.